Lesson 12.3 is maximum and minimum points and optimization. I would pause the video and write down these notes. So a stationary point is a point that is neither increasing nor decreasing. So it has an instantaneous rate of change of 0. So if f prime of c is 0, then c f of c is a stationary point. So if you look over here, this red curve is our original function, and the blue curve is the derivative. So at these two places, our derivative is 0, and at those two places on the original function, the slope is 0. The local maximum is a point where the graph changes from increasing to decreasing, or a positive slope to a negative slope. So right here we'd have a local maximum. It goes from increasing to decreasing. A stationary point is a local maximum if the sign of the derivative goes from positive to negative. So it's going from increasing, a positive slope, becomes 0 for one instantaneous second, and then goes to decreasing, or a negative slope. So here on the derivative, we see it goes from positive 0 to negative, and on the original function, it goes from increasing to decreasing, so therefore that's a local maximum. A local minimum is a point where your graph goes from decreasing, or a negative slope, to increasing, or a positive slope. So a stationary point is a local minimum if the derivative goes from negative to positive. Negative slope for decreasing instantaneously becomes 0, that's your stationary point, and then becomes positive. So decreasing or negative slope, 0, increasing. A global max or min is the one largest or the one smallest point on the entire graph for the given domain. So in this example, we have s equals 3t cubed plus 2t squared minus 4t plus 2. And we want to find ds dt, so the derivative of s with respect to t. We want to sketch the function s equals 3t cubed plus 2t squared minus 4t plus 2 and its derivative on the same axes. And then we want to solve the equation where the derivative is equal to 0. So go ahead and pause the video and do parts A through C. So first I found the derivative using the power rule. So bring the power down in front, reduce the power by 1. You end up with the derivative to be 9t squared plus 4t minus 4. And then the graphs on the previous slide were actually these two graphs. So the red line, or red curve, is s, and the blue curve is ds dt. So then to find where these two things, or where the derivative is equal to 0, I set this equal to 0. It doesn't factor, so I just used my graphing calculator, and I found that the two places where this equals 0 is that t equals negative 0.925 and 0.481. So then using the notes on the previous slide, determine whether or not these 2 points are local maxima or local minima. So go ahead and pause the video and try part D. So looking at the graph, x equals negative 0.925 is a local maximum, and the y-coordinate is 5.04. So you can see here easily it goes from increasing to decreasing. You can also say that the derivative goes from positive to negative, so increasing to decreasing, positive to negative, so therefore it's a local max. 0.481, 0.873 is a local min because the graph goes from decreasing to increasing, or your derivative goes from negative to positive. Part E says the domain of the function is now being restricted from negative 2 to 2, and we want to find the actual maximum and minimum values. So the global max and the global min, so the one highest point on the graph and the one lowest point on the graph. So this can occur at endpoints or at local max and min. So you have to test your endpoints, so negative 2 and positive 2, and compare them to your local max and min, and figure out which of those 4 is the highest point and which of those 4 is the lowest point. So go ahead and pause the video and try part E. So the first thing I did was I found the y-coordinates at negative 2 and positive 2 for the original function, and the y-coordinate at negative 2 is negative 6, and the y-coordinate at positive 2 is 26. And then our local max from part D was a y value of 5.04, and our local min was a y-coordinate of 0.873. So we want to find the absolute biggest out of the 4 of these, which is 26. So our global max is 2, 26. And then the absolute smallest out of the 4 of these is negative 6. So our global min is going to be negative 2, negative 6. So in this case, our endpoints were our global max and our global min. They could have also been one of our locals as well. So this next function, we have y equals x plus 1 over x, where x does not equal 0. So we want to find the expression for dy dx, the derivative, sketch the curve, and find the coordinates of any local max or local min points. So go ahead and pause the video and do parts A through C. So I found the derivative using power rule. 1 over x is the same thing as x to the negative 1 power. So dy dx is 1 minus 1x to the negative 2, or 1 minus 1 over x squared. And then sketch a graph. Here's the graph of x plus 1 over x. And then find any coordinates of local max or local min. So I used my graphing calculator, and I found that the local max is at negative 1, negative 2, and the local min is at 1, 2. Now what we want to do is we want to find the gradient of 2 points close to but on either side of our minimum. So our local min was at x equals 1. So you want to pick a point that is slightly less than x equals 1, like x equals maybe 0.5, and something bigger than x equals 1, like 1.5, and find the gradient of those 2 points. So go ahead and pause the video and try that. So again, I chose 0.5 and 1.5, something that's just slightly on either side of x equals 1. So if I plug 0.5 into the derivative, because I want to find the gradient, I get negative 3, which is negative. So my slope is negative for things that are slightly less than x equals 1. And then I also plugged in 1.5, and I end up with 0.556, which is positive. So for x is slightly bigger than x equals 1, your derivative or your gradient is positive. So if my derivative goes from negative, which means the original function is decreasing if you have a negative slope, and it switches to positive, which means my original function now is increasing, if I go from decreasing to increasing, that is why we have a local minimum. So this is a good way here to organize when you're doing these to decide whether something's a local minimum or a local maximum. So again, it's a local minimum because your derivative goes from negative to positive, which means your slope is going from negative to positive, which means your original function is going from decreasing to increasing. We can use this to help us with optimization problems like we talked about a few chapters ago. So optimization is maximizing or minimizing values in given models. So we did this before, but we used our graphing calculator. Now we can use calculus. So a can of dog food contains 500 centimeters cubed of food. The manufacturer wants to receive the maximum profits by making sure the surface area of the can has optimum dimensions. Let the radius of the can be r and the height be h. And we want to find the dimensions that minimize the surface area. So here's a little picture. We have our cylindrical can. The volume of a cylinder is pi r squared h, and the surface area, if it has a top and bottom, is 2 pi r squared plus 2 pi r h. So the first thing we need to do if we want to minimize surface area is we need to write it in terms of just one variable. So we need to get rid of either the h or the r. So using what you know about the volume being 500 centimeters cubed, write an expression for the height in terms of the radius. So if pi r squared h, which is the volume, is equal to 500, which is what they tell us, then if I divide both sides by pi r squared, I end up with h to be 500 over pi r squared. So now I can take this and I can plug this in for h in my surface area equation, and I can now have surface area in terms of just the radius. So I plugged in h is equal to 500 over pi r squared and for h, and I end up with a surface area function of 2 pi r squared plus 1,000 over r. This is now something that we can maximize using calculus. So instead of using our graphing calculator, we're going to maximize this using calculus. So the first step would be to take the derivative. So take the derivative, find s prime of r. Pi is just a constant, so just treat it like a constant. So we found that the derivative s prime of r is 4 pi r minus 1,000 over r squared. And maximum and minimum occur at stationary points. And stationary points occur when your derivative or your gradient is equal to 0. So go ahead and pause the video and find the value for the radius that would make this true, be our stationary point. So I set this thing equal to 0 and solved for r. You could have used a graphing calculator. I did it by hand. So I moved the 1,000 r squared over, multiplied both sides by r squared, divided by 4 pi, and so you end up with the cube root of 1,000 over 4 pi, which is 4.30 centimeters. Since this is the only stationary point, this would have to be our solution, but I want to test just to make sure that it really is a local minimum to minimize this surface area. So what I'm going to do is I'm going to test a point that is slightly smaller than 4.30 and slightly bigger than 4.30 and check to see if my derivative goes from negative to positive or my original function goes from decreasing to increasing. So I tested a point that was slightly smaller. I tested r equals 4, and I found the derivative at r equals 4 to be negative 12.2. So that's negative, which means your original function is decreasing. And then I tested something slightly bigger than 4.30. I tested r equals 5 and got 22.8. So my slope was positive, which means my function is now increasing. So I went from decreasing to increasing. So this is really the local minimum that we want. So we now know that we want our radius to be 4.30 centimeters. So just pause the video and find the height. So we knew up here that height was 500 divided by pi times the radius squared. So I just plugged in 4.30 for the radius, and we end up with a height of 8.61 centimeters. So the dimensions that give us a volume of 500 cubic centimeters, but minimize surface area, which would therefore minimize cost and maximize profits, would be a radius of 4.30 centimeters and a height of 8.61 centimeters. So optimization, finding maximums and minimums. Minimums occur when your function goes from decreasing to increasing, which means your derivative goes from negative to positive. Maximums occur when your function goes from increasing to decreasing, so where your derivative goes from positive to negative.